Hey guys, in this lesson we're going to be studying solubility factors and basically just what affects solubility, which is the ability to dissolve. The homework associated with this lesson is here, questions 5 and then 7 through 11 on pages 120 to 121. That should be the heading of your classwork page, and the second thing on your classwork page should be this aim. What factors affect the solubility of solutes and solvents? And then, underneath the aim, copy down these 2 now questions, but don't answer them. We'll do them in class. All right, so solubility factors. You should know that when we make coffee, that part of the coffee does dissolve in the water. But, as you know, the grounds do not completely dissolve. I recently read that only about 1/5 of each coffee bean will actually dissolve in the water, which means that 4/5 of the coffee don't dissolve. So check this out. If I pour a few tablespoons of coffee grounds into a pot of boiling water, what will happen next? But what we know about the coffee grounds is that if only about 1/5 of the bean dissolves, that means that the bean has some substances in it which are able to dissolve in water, but it has other substances which are not able to dissolve in water. All right, now this part may sound a little bit crazy, but imagine that I use a spoon to transfer some sugar to the mug of coffee, and then I use the spoon to stir it in. Now, of the 2 items, the spoon or the sugar, which one will dissolve in the coffee? So obviously, it's the sugar, but I do think it's worth wondering why the spoon does not dissolve if the sugar does. So this brings up 2 words, soluble and insoluble. Soluble means that a substance is able to dissolve in a solvent, and insoluble would mean that a substance is not able to dissolve in a solvent. All right, so on these next few slides, we're going to talk a little bit about the factors that actually affect whether a substance is considered soluble or insoluble. And in my opinion, the most important effect, or the most important factor that can affect solubility is whether or not the substance is polar or ionic. Both being polar and being ionic can have enormous effects on solubility. Here's how. So what polar molecules and ionic compounds have in common is that they have a charged portion. For the ion, the entire thing is charged, like right here. Here's a chloride ion, it's totally charged. Here's a sodium ion that's totally charged. But over here we've got like a water molecule, and it only has partial charges. We have slight positive near the hydrogens and slight negative near the oxygen, but they are both charged. And as we know, positive and negative charges attract each other. So when we answer the question, why is NaCl able to dissolve so easily in H2O, we should imagine the way the charges interact. So, for instance, the negative end of the water molecule will be very attracted to the sodium ion whose charge is positive, and it will be able to pull that sodium ion off of the crystal. Similarly, the hydrogen end of another water molecule, which is slightly positive, would be very attracted to a chloride ion, which has a negative charge. And so these opposite charges are able to pull ions off the crystal. When all of the ions have been pulled off the crystal, we would say that the crystal has dissolved, and the ions have dissociated, and they have formed new relationships with their polar molecules. This is also considered a form, or at least an effect, of molecule-ion attraction. We can also make a sort of qualitative judgment about the attraction that hydrogen has to chloride and that oxygen has to sodium versus the sodium to chlorine attraction. While the attraction within an ion is extremely high, you can combine the mobility of the liquid water with its attraction to the ions to consider that the ions in the crystal simply would prefer to be associated with the water molecule. So that says something about the strength of the attractions, although it maybe doesn't say, at the end of the day, that the attraction is greater. And the only other thing that we need to add to this slide is that polar solutes are going to be soluble in polar solvents because they both contain charges, and therefore solubility would be possible. But a polar solute would not be soluble in a nonpolar solvent because the polar solute would need charges to be attracted to the nonpolar solvent, and the nonpolar solvent doesn't have those. Similarly, if you had a nonpolar solute, it would not be soluble in a polar solvent because this guy doesn't have charges. But this would be soluble in a nonpolar solvent because since neither one of them has charges, they could simply mix together. If you have an ionic solute, it would dissolve in a polar solvent, and in fact, this example is exactly that, an ionic solute, the sodium chloride, dissolving in the polar solvent. Because they're both charged, it's soluble. But an ionic solute in a nonpolar solvent would not dissolve because the nonpolar solvent would not have charges, and therefore this charged guy could not dissolve here. In short, what a lot of chemistry teachers would tell their students is that like dissolves like, meaning essentially that a polar solvent and a polar solute would be dissolved because they're very similar. A nonpolar solute, nonpolar solvent would dissolve because they're very similar, and ionic solute with polar solvent would dissolve because they're very similar. So like dissolves like. Pressure is the result of collisions between gas molecules, or actually any molecule, and the walls of their container. Now, pressure has the ability to affect the solubility of certain substances, namely gases. However, it is worth noting that pressure does not affect the solubility of solid or liquid solutes. The reason for this is that solid and liquid solutes are so densely packed that the addition or removal of pressure would not alter their formations. So if I had to choose, I would say my favorite soda is Diet Coke. But it's pretty also famous for uncapping it and making a really delightful fizzing noise when it's uncapped. This is an instantaneous decrease on the pressure in my soda, pressure being the collisions. The gas that was previously dissolved in the liquid, which was carbon dioxide gas, is released into the atmosphere as a result of the drop in pressure. Another way you can think about this is to visualize what this diagram is showing us. So the dark blue dots are the gas molecules. They would be going through collisions and causing pressure inside the container. But if I were to decrease the volume of the container by adding pressure to this piston, you would notice that the gas molecules in the area above the level of the liquid would be forced down into the liquid, meaning that the solubility of the gas in the liquid would increase very much as pressure was increased. So increasing the pressure is going to force air molecules into the liquid, in other words, making the liquid more soluble for gases. Now, using the kinetic molecular theory, we can explain why this is happening. The kinetic molecular theory says that the distance between gas particles is very large, which means that they are compressible. And it's really this fact that means that the addition of pressure can change the solubility of a gas. Alright, so we can also look at the effect of temperature on solubility. I will point out right away that the effect of temperature is different for solids in liquids than it is for gases in liquids. I'll use these diagrams to help explain. So if we start with a solid which is sitting on the bottom of a beaker waiting to be dissolved, we can think about how it would change with the addition of heat, or as it's cooled with the reduction of heat. So these particles are sort of sitting on the bottom of the container because they're, busy being solids. But if you heat them up, You're going to give them the energy they need to fly up into the solution, therefore becoming dissolved, which is another way of saying that we're increasing the solubility. So if we add heat, you're going to find more particles like this. However, as the substance is cooled, you'll notice that they will want to settle back down at the bottom of the container. This would be a result of losing their kinetic energy through the cooling process, and you would see a reduction in solubility as a result. On the other hand, let's consider a gas which is dissolved into a liquid. The gases that are already dissolved in the liquid have more energy and more motion already than the solids did. So they're already wanting to spread out. This is part of the kinetic molecular theory, that the gases want to spread out. If you were going to give them even more kinetic energy, you might find that the gas particles would escape the liquid altogether. You know, gases being gases, they might go up into the atmosphere. This, in fact, would be a reduction in solubility, because as the gases left the liquid and go into the atmosphere, you would find that you would have very few left behind here, just like this. And so the kinetic molecular theory is telling us that since the gases are already very spread out, that increasing their kinetic energy reduces their solubility. But since solids are so compact, increasing their kinetic energy will increase their solubility. And so we finally reached the pair-up. Please copy down these questions, but don't answer them. We'll answer those in class. And for the summary, please copy down this summary, and don't answer it. We'll answer them in class. I may need to show you this animation again, which I have shown you before, but you could sketch it if you wanted. Thank you, and have a good night.